Looking again at our familiar equation, AX is equal to C, we're now going to discuss two other interpretations of this. In other words, AX equals C could be interpreted as a transformation of vector X into vector C, but it could also be interpreted or could be used to describe X in a changed X that is originally defined in one basis and describing it in a new basis. After taking careful notes of this video, you will be able to transform a vector x to a new vector by a linear operation, a times x, or in this case, q times x, a and q both being square matrices. You'll be able to take a vector originally defined in one basis and show what that vector is in a rotated basis. And last, you'll be able to determine whether a matrix A or Q is orthogonal or not. So let me write down these two interpretations of the general equation AX is equal to C, or generally the multiplication of X by a square matrix being equal to another vector. So I'm using this expression for that general operation. And interpretation 1 is that X is being transformed to a new vector C. And the alternative interpretation, or another interpretation of that operation, is X is being described in a new basis. So those are two interpretations that I'd like to develop conceptually here, side by side. So you can imagine we have a basis E1, for example, and E2, and we're describing a vector in that basis, that vector being, but multiplying X by matrix A produces a transform vector. And it is a vector of, in generally, different magnitude and direction. And this is, of course, an illustration in 2D space. But this concept applies to ND space. Okay, so that's an illustration of interpretation 1. Or alternatively, vector X is originally described with one set of basis vectors, or one basis. And in that basis, we would write vector X as X bracketed with a lowercase b to describe x in one basis, but then x is described in another basis. So we would take x described in one basis and multiply it by a matrix, and that would give the resulting same vector in another basis. And I'll illustrate that below. So let's look at the special case of just rotation. So for the first interpretation, in which we're involving just rotation, we would have our original vector x, say, and if we multiplied x by the appropriate matrix, we could get, oh, I better draw x a little bit higher up. So x is originally here, and we could transform x by just rotating it clockwise by angle theta. And that could be done by multiplying it by the appropriate vector. So in this case, ax rotates x clockwise by angle theta. Now to illustrate the second concept, let's define our first set of base vectors, E1 hat. Well, yeah, they're unit vectors, E1 hat and E2 hat. And we have x defined in that system. Yeah, let's see, I'll keep with the blue here. Right, x in the first basis, and with this first basis, the component in the E hat 1 direction will have a certain value, and the component in the E hat 2 direction will have a different value, and that would define x in this basis. So here we have our original basis again, E1 hat, E2 hat, and now I'm going to describe x in a rotated basis, E1 hat prime, and E2 hat prime. And this same vector, I'm going to try to draw it in the same, having the same length and same direction as shown in the first picture. This same vector is now being described in a rotated coordinate system because it will have a different value in the E hat 1 prime direction than in the original, and it will have a value in the E hat 2 prime direction. And in this case, the coordinate system is rotated in the counterclockwise direction. And so A times x defined in one basis gives x defined in another basis. So let me write this down. So A times x defined in one basis defines x in a basis rotated in the counterclockwise direction by angle theta. Okay, and in these two cases, A is the same matrix. So AX can be interpreted as a rotation of vector x by angle theta in the clockwise direction, or it can be represented, AX can represent the vector described in a rotated system rotated by theta in the counterclockwise direction. And just to nail that concept home, you might be able to see that if we were to highlight the rotated vector like this, the yellow arrows here could be matched up with the yellow arrows here, so that in this case, this is the first component of the rotated vector, and this is the second component of the rotated vector, and these are equal to the components along the E1 hat prime axis in this case and the E hat 2 prime axis in this case. Now let's consider the second interpretation, the change of basis, and this is covered on in section 10.7 of Greenberg, and I'm going to focus on this interpretation to develop the matrix this matrix A that accomplishes this change of basis. And you can refer to this diagram, which is a simple sort of illustration in 2 dimensions. So again, vector x can be described in the first basis, and I'll see if I can remember to use the blue color for the first basis, as equal to x1 e1 plus x2 e2. This is a linear combination of the base vectors in basis 1. So this is the first basis, and for example, in 2D, this would correspond to the blue vectors in the diagram. X can equally, that is the same vector, can be equally well described in a rotated basis, as x1 prime e1 prime plus x2 prime e2 prime. So the x's have different values because the base vectors are in different directions, and they may have, in fact, different magnitudes. So the question we're going to address is how are the values in one basis related to the values in the rotated basis? To answer that question, we can note that each base vector in the first basis can be expressed as a linear combination of each basis vector of the second basis. In other words, E1 can be expressed as a coefficient Q11 times E1 prime plus another coefficient E21 times E2 prime all the way out to QN1 times EN prime. And this can be done for E2 all the way out to E3, all the way out to EN, again being a coefficient Q1n this time times E1 prime plus Q2n E2 prime all the way out to QNN EN prime. And this can be written as the ith vector, base vector, is the linear combination, which is the sum of Qji times EJ prime. And we're summing over J here. Now, substituting these expressions for the original base vectors into the first equation, we can now start to relate x1 to, or each of the x's in the first basis to each of the x's in the second basis. So again, making the substitution, we get x is equal to x1 times E1, which is again Q11 E1 prime plus Q21 E2 prime all the way out to QN1 EN prime plus all the other terms out to xn times En, which is Q1n E1 prime plus Q2n E2 prime all the way out to QNN En prime. And let's collect terms multiplied by each unit or each base vector. And we see that x is equal to x1 Q11 plus x2 Q12 all the way out to xn Q1n, and that's all multiplied by the base vector, the first base vector in the rotated system, or the different system, modified system. And this is summed for each of these modified base vectors all the way out to the nth one. And what you can perhaps recognize now is that we have an expression for x in terms of the changed basis, and so there, and that's the same as the second equation. So each of these terms is now x1 prime, the primed x values. So this shows that x1 prime is a linear combination of all the x's, all the elements of the vector in the first basis. And likewise, xn prime, the last element in the transform basis, is a linear combination of all the x's in the original basis. So in other words, x1 prime is equal to this linear combination, which I can write as a sum, and the sum is over j of q1j xj. So that's just an alternative way of writing this first summation here. And x2 prime is likewise the sum for j equals 1 to n of q2j xj. And this can be carried out all the way out to xn prime, being the sum again over j of qnj xj. Or in other words, the ith component of the transform system, xi prime, is equal to the sum over j of qij times xj. And this is our system of equations. This is x described in the transform basis being equal to a matrix, which we'll call Q, times x defined in the original basis. So here the matrix Q is has the ij element of matrix Q is little q ij, and we could redefine these variables as this, with this being c or xb prime representing or being x described in the changed basis b prime. So now let's figure out how to determine what each of these components of this transformation matrix is. And here we're going to consider for b and b prime being orthonormal. In other words, the base vectors are all unit vectors and they're each orthogonal to each other. To answer that question, let's go back and remind ourselves that the unit vector in the each unit vector in the reference system is a linear combination of the unit vectors or the base vectors in the change system, and they're related to each of these components of the transformation matrix. So I'm going to write that one equation down again. So in this case, we're dealing with unit vectors. So E1 is equal to the sum for k. I'm going to use k as the summation indice. and we have QK1, and the base vector for the um, change system. So that's EK prime. And what we have to do is isolate each of these individual Q's to see how they relate to these base vectors. So let's have a look at what happens if we take the dot product of E1 with with say the jth primed basis vector. So J, of course, could be 1, it could be 2, it could be any number, but we'll just leave it as a placeholder as J. And when we show that with the sum, we have QK1 EK prime dotted with EJ prime, E hat J prime. And remember that these are orthonormal vectors, so the dot product of E hat K with E hat prime J is equal to 1 when K is equal to J, and 0 when K is not equal to J. And K, as we do this sum, K is only equal to J once. It's only it's equal to J when it's only equal to J, and so there's only one value of Q that remains, and that one value of Q is Q J1 when we evaluate this sum. And so this tells us that E hat 1 dotted with E prime J is equal to QJ1. We could do the same thing for any value of any base vector, E hat I, and if we dotted that with E hat J prime, again, each vector I is a linear combination of the Q's, so we have QI EK hat prime, and then so this is each base vector as a linear combination of the base vectors for the primed system, and then we're dotting it with EJ hat prime, and again E hat K dotted with E hat prime J is equal to 1 only when K is equal to J, and 0 when K is not equal to J, again because they're orthogonal vectors and they have unit length. And so when we sum over K, the only remaining term is QJI. And so this tells us that QJI is equal to the ith base vector for the unprimed system and the jth base vector for the primed system. So in other words, Qij, each component of the transformation matrix, is equal to Ei prime dotted with Ej hat. And so again, with Q having components Qij, each of those components is the dot product of these particular base vectors. Okay, so that's the result. Now let's look at what that means. Oops, let me correct this equation here. This is an I. So let's look at what each of those terms means. So Qij is equal to the ith base vector in the reference system dotted with the in the ith unit vector in the change system and the jth unit vector in the reference system. And E hat prime I dotted with E hat j is equal to the magnitudes of those two vectors, and they're both unit vectors, so the magnitudes are 1 times the cosine of theta ij, and theta ij is the angle between the ith unit vector in the transform system and the jth unit vector in the reference system. So each component qij is so it's the cosine, the cosine of the angle between each of these unit vectors. Okay, so let's look at a case of 2D rotation. And so we have x described in the transform system being equal to Q, our transformation matrix, times x described in the reference system. So I'll sketch that again. So we have E1 in the reference system and E hat 2 in the reference system. And the rotated system is oriented at an angle theta, and this is E1 prime, E hat 1 prime, and this is E hat 2 prime. And so let's build our Q matrix. So Q, again, is the angle between E hat 1 and so it's the cosine of the angle between these two vectors. And so that gives cosine theta, because the angle between these first two unit vectors is just theta. And then the 1, 2 component is equal to the cosine between E1 prime and E2. And this angle is pi over 2 minus theta. And so this is cosine pi over 2 minus theta. E hat prime 2 dotted with E hat 1 is equal to the cosine between the E hat 2 prime and E hat 1. And this angle is, let's see if I can squeeze that in there. And that is equal to pi over 2 plus theta. And finally, we have E hat prime 2 dotted with E hat 2. And that's this angle, and this is theta. And so we have cosine of theta. And so if we use our trig identities, we have cosine theta. Cosine of pi over 2 minus theta is equal to sine theta, and cosine of pi over 2 plus theta is equal to minus sine theta. And then the last term is cosine theta. So our Q matrix, due to a rotation of the basis by clockwise angle theta, or counterclockwise angle, is this matrix right here. And so this brings us back to when we introduced the concept. The matrix that we just defined is what we called Q, and Q, if we set that equal to A in our equation right here, then this is how we describe, again, x in the rotated basis as a function of x in the reference basis. And this is if the basis is rotated counterclockwise by angle theta. And the same operation, that is multiplying q by x, or we've set a and q equal to each other by x, and if we set that to a new vector c, then this same operation can be interpreted as rotating x into a new vector c by an angle theta in the clockwise direction. So now the last important aspect of Q, again, this is the rotation. I should say this is the matrix that performs a rotation for interpretation 1, or a change of basis between two orthonormal bases. Okay, and that change of basis is, since they're both orthonormal, it's a rotation of the bases by angle theta. So this is what Q is. And one important aspect of Q is that Q transpose times itself is equal to the identity matrix. And what that means is that the transpose of Q is equal to the inverse of Q. So, and matrices having this property are said to be orthogonal. So an orthogonal matrix is a matrix in which its transpose is equal to its inverse. And one way that you can interpret Q is it rotates a vector clockwise, or a basis counterclockwise by theta. And a simple interpretation of Q transpose or Q inverse is it does the opposite. It rotates a vector counterclockwise, or a basis clockwise by theta. So one rotates it in one direction, and its transpose or its inverse rotates it in the other direction, so that when you multiply the two, there's no rotation at all. So the vector remains the same, or the basis stays the same when you multiply the two together to produce the identity matrix. Okay, so that concludes this video on AXC as a vector transformation or a change of basis.